We're talking about investigating the current voltage, or IV, characteristics of different circuit components. Before we even think about the graphs, we need to have a really solid grip on the three main players in any circuit. That's voltage, current, and resistance. We want to find out the relationship between the potential difference, you can think of that as the push, and the current that results from it, the flow, for a few different components. First up, potential difference, which, we usually just call voltage. The easiest way to think about it is as the electrical oomph or pressure that gets the electrons moving around a circuit. Simple as that. No push, no flow. And that flow of electrons, well, that's what we call current. We measure it in amps, and it's literally just telling us how much charge is zipping past a certain point every single second. Now, you'd think that a bigger push from the voltage would mean a bigger flow of current. But, as you're about to find out, it's not always quite that simple. You see, that flow isn't always a smooth ride. Resistance is basically how much a component fights back against the current. It's trying to slow those electrons down, and we can work it out using the absolutely essential Ohm's law equation. Resistance equals potential difference divided by current. Not all components resist in the same way. Some are called ohmic conductors. Their resistance is steady and constant. But others are non-ohmic, and that means the resistance actually changes as more current flows through them, usually because they start to heat up. Okay, let's get our hands dirty and look at the practical method. We've got our power supply, of course, wires, the component we're testing, and then the really important stuff, an ammeter to measure the current, a voltmeter for the potential difference, and a variable resistor which lets us change the voltage going across our component. You have to remember the ammeter goes in series. That means it's in the main loop of the circuit, so all the current has to flow through it to be measured. The voltmeter, on the other hand, goes in parallel. It sits across the component to measure the difference from one side to the other. The actual method is pretty straightforward. First, build the circuit correctly. Then use your variable resistor to get the lowest possible voltage reading and write down that pair of values for V and I. After that, you just nudge the variable resistor a bit to increase the voltage, take another set of readings, and you just keep doing that to build up a good set of data. Oh, and for the diode, you've got one extra step. You need to swap the wires on the power supply to see what happens when you try to send the current the other way. We take all those pairs of V and I readings, we plot them on a graph, and the shape that graph makes, its IV characteristic, tells us basically everything we need to know about how that component behaves. So for a standard resistor, as long as it doesn't get hot, you get this perfect straight line going through the origin. This is literally a picture of Ohm's law in action. The current is directly proportional to the potential difference. Now, for you guys aiming for those top marks, here's a little trap to watch out for. On an IV graph, the resistance is actually 1 divided by the gradient. That means a steeper line actually has a lower resistance. Don't get caught out. Now, the filament lamp, that's a whole different story. Its graph starts off straight, but then it curves over and gets shallower. Why? Well, as the current flows through that tiny filament wire, it gets seriously hot. This makes the metal ions inside the wire shake about like crazy, creating a massive traffic jam for the electrons trying to get through. So its resistance goes up. And then we have the diode. If you try to push current through it the wrong way, the reverse direction, its resistance is massive and pretty much nothing gets through. But if you push it the right way, the forward direction, as soon as you hit about 0.6 volts, the resistance just collapses and current floods through. It's basically a one-way street for electricity. Let's focus on turning this practical knowledge into actual marks on the paper. Examiners, they just love to ask about what could go wrong and how you could make the experiment better. So for the filament lamp, you have to talk about controlling the temperature, maybe by switching the power off between readings to let it cool. With any analog meter, you've got to avoid parallax error, which just means making sure you're looking at the meter dead on, right at eye level. And always check for zero error before you start.
So how would you tackle a question like this one? Well, you've got to hit the key points. You'd say that the current makes the filament heat up. That gives the metal ions more kinetic energy, so they vibrate more. This means they collide more often with the electrons trying to flow past, which impedes their path, and therefore increases the resistance.
Just burn them into your brain. Resistor, straight line. Lamp, S-curve. Diode, flat, then a vertical wall. If you can sketch these 3 graphs and explain what they mean, you're well on your way. And I'll leave you with this little puzzle to chew on for your revision. Think about a thermistor. That's a component whose resistance actually goes down when it gets hotter. So if you were to plot its IV graph, what do you think it would look like? How would its curve be different from the filament lamps? Have a think about that one.